there, it's Shannon Mapchick-Myers. I hope you're having a wonderful morning, afternoon, or evening whenever you're watching this show. And today we will be checking out Pascal's formula and the binomial theorem. So let's get started. Pascal's formula. So you probably are familiar with Pascal's triangle. It's an extremely useful tool for expanding binomial sums and differences. Pascal's formula is crucial for the algebraic proof of the binomial theorem. So let's take a look at some of these formulas. So recall the following formula. N choose R is equal to, the notation N choose R, and that is N factorial divided by R factorial times the quantity N minus R factorial, where N and R are non-negative integers and R is less than or equal to N. So please compute the following. If we were to write all this out, this first one would be equivalent to N factorial divided by N factorial times the quantity N minus N factorial, which is, we can divide out these N factorials to be 1. We would have 1 over 0 factorial. And remember, you get the multiplicative identity for 0 factorial, and that is 1. So N choose N, long story short, is 1. So now if I choose N minus 1 groups from N, I will have N factorial divided by quantity N minus 1 factorial. And then I subtract from N minus 1, and all of that is to the factorial. So, or not to the factorial, it's in a factorial. So now I know I need to divide out that N minus 1 factorial, so let's rewrite N factorial as N times quantity N minus 1 factorial. So this here, these two are equivalent, and that will be over N minus 1 factorial. N minus N is 0, right? And then minus 1 is going to be 1. So I would just have 1 factorial, which is 1. So dividing out the factorials, I just get N. Groovy? All right, beautiful. Next up, N choose N minus 2. So that's going to be N factorial over quantity N minus 2 factorial times N minus quantity N minus 2, all wrapped up in one happy factorial. So again, I know I'm going to have to factor out, I want to get rid of that N minus 2 factorial, and I have the ability to do that because factorials are decreasing factors. So I'm going to change that numerator again. N times N minus 1 times N minus 2 factorial all over N minus 2 factorial. And then N minus 2 gives us positive 2 factorial. And so again, matching up the N factorial to this expression here in the numerator, the N minus 2 factorials divide out to be 1. 2 factorial is 2, and then I end up with N times quantity N minus 1 over 2. Groovy, huh? All right, so next up, is there some other way that we could write N choose R? Sometimes we split things up and make them more ugly and be able to do a proof. So I know this looks beautiful, choosing R from N, but let's see if we can mess it up a little so that we can prove our binomial theorem, right? So is there some other way we could write n choose r? Let's say we have some set A. So this here, this whole thing is the set A. So suppose A is a set with n elements. And B is a subset of A and contains R elements. So recall that you've got B in here. Let's just, I don't know, put a line down the middle, or roughly the middle. Let's say that right here is set B. And we know that set B, so the whole thing is set A. And set B is just this part, and B has R elements. Well, instead of naming the other set C, we could do that subtraction of sets, right? Where this part of it would be A and not B. And so how many elements would that have? We know there's how many elements in A? Beautiful, N. And then we would take away the R elements that are in B. Perfect. So another way of saying n choose R would be, beautiful, n choose n minus R. So looking at this and showing algebraically, what we could do is this. We could say, let's check out what n choose n minus R looks like when we write it out. This would be n factorial divided by n minus R factorial times n minus quantity n minus R, all of that factorial, which would give us n factorial over n minus R quantity factorial. N minus R gives us a positive R factorial. And if you just flip it around, isn't that n factorial over R factorial times n minus R factorial? Pretty groovy, huh? Which is what? Equivalent to n choose R, right? So yes, n choose R can be rewritten as n choose n minus R. So let's take a look at Pascal's triangle for values of n choose R. So I know that you've kind of built up Pascal's triangle before in algebra, but let's just check it out in a different way. We always know that if you are, 0 choose 0, right, is just going to be 1. So we're looking at the n choose R. So the n goes down vertically, the R goes across horizontally. So 0 choose 0 is 1. So I'm going to go down here. And then if I'm choosing 0 subsets of 1, there's only one way to do that. So this whole row, or column rather, I would end up here with n choose 0, which is all just 1. This would be n plus 1 choose 0. Cool? And then on and on and on. Now, you can't have choose one set out of, one there's zero ways to choose 1 from n. So that all of these across on that first row are not applicable, right? So let's check out 1 choose 1 is 1, right? But 1 choose 2, again, r has to be less than or equal to 1. So these are all not applicable. They don't make sense. They are undefined. 2 choose 1 is 2. But you can't, and then 2 choose 2 is 1. Cool so far? And then, actually on this row, sorry, I didn't mean, I'm keeping that blank. I have an evil plan. And then again, all of these won't make sense. All right, 3 choose 1. Beautiful. 3 choose 2 is, again, 3. And then 3 choose 3, there's 1 way. And then the rest of these don't make sense. And continuing on, if we take a look at 4, choose 1 is 4. 4 choose 2. So how many ways can we choose 2 from 4? You'll find out that that is 6. All right. And then 4 choose 3 is 4. And we have 1. Now, here's the kind of cool stuff. So now we have 5s. Oh, and all of this is stuff that won't make sense. All right, so now we have 5s. 5 choose 1 is 5. And notice how they're all going up here. And then we have 5 choose 2. Well, just in case you weren't sure, if you add the terms in the middle here, right? Sorry. If you add the terms here, 6 plus 4 is 10, right? But isn't 5 choose 3 the same as 5 choose 2? Because you could use that formula we just learned, the fact that n choose r is the same as n choose n minus r. So this here will also be 10. And then we come down here, we get 5, we get 1. These don't make sense. So there's a pattern here. So the next one, you keep going on, right? You'll get to n choose 1, which is what? Beautiful, it's just n. You'll get n choose 2. You'll get n choose 3. N choose 4. N choose 5. And you'll keep going on and on and on until you get to n choose r minus 1. And then n choose r. Now, using the same idea here as we did before, right? We could make a little L shape way down here to see the trend. All of these continued on, right? So, continued on in the same manner. So before we look at that box there, right, let's take a look at the trend going this way. So on this row, we would have n plus 1, choose 1, n plus 1, choose 2, n plus 1, choose 3, n plus 1, choose 4, going along and along, n plus 1, choose 5. And if you keep going in that manner, what'll happen is we will end up getting n plus 1, choose r. And we'll prove that momentarily. In our proof of the binomial theorem. Or binomial theorem, sorry, the Pascal's formula. All right, we'll prove that in Pascal's formula because that's what Pascal's formula is. Isn't that groovy? So if n and r are positive integers and r is less than or equal to n, it turns out that n plus 1, choose r, is equal to n, choose r minus 1, plus n, choose r. And as you notice, that's what we had gotten up there. So let's take a look at the algebraic version of the proof. Let n and r belong to the set of positive integers, and r is less than or equal to n. So looking at the expression that we have, n choose r minus 1 plus n choose r, let's check out what that is equal to. So we'll have n factorial over r minus 1 factorial times n minus quantity r minus 1, all n factorial, plus n factorial over r factorial times n minus r quantity factorial. Cool so far? All right, and this in turn will be equal to n factorial over r minus 1 quantity factorial. N minus quantity r minus 1 is going to be n minus r plus 1, all in factorial, plus n factorial over r factorial times n minus r quantity factorial. Cool, cool? All right, now we just need a common denominator, right? So actually, I'm going to move that over a little since I can and show you how we're getting our common denominator. So if we multiply, the first one is missing a factor of what? So if we wanted to match, which one is bigger, r minus 1 factorial, remember these are all products, or r factorial? Beautiful, r factorial. So if we multiply that first fraction by r over r, what'll happen is r minus 1 factorial times r is just r factorial. Isn't that beautiful? So we've got that one set up. Now, looking at n minus r plus 1 factorial, right? What is the larger? Awesome, n minus r plus 1. But that plus 1, you know, it's not as easy to do as that first one, so we're just going to do that whole thing. So we're going to go and do Now, if you take a look at n minus r plus 1 factorial and n minus r factorial, if we were to multiply the second one by a factor of n minus r plus 1 over n minus r plus 1, we will end up getting n minus r plus 1 factorial. Isn't that groovy? All right, so now continuing, we'll have n factorial times r over r minus 1 factorial times n, whoops, sorry, I'm putting it under that common denominator now. So r factorial times n minus r plus 1 factorial. So that's the common denominator. So I'm going to need to add plus, so I'll show where I've added the common denominators in a different color. So the r was part of getting the common denominator for that first fraction. And then we had n factorial times n minus r plus 1. Cool, cool? All right. So let's take a look at what we have going on. This will be equivalent to n factorial. There's a common factor of n factorial. So I have a factor of r remaining in the first term. And in the second term, I'd be adding n minus r plus 1 over our same denominator, r factorial, times n minus r plus 1, that quantity factorial. Do you see that n factorial times quantity n plus 1 is n plus 1 factorial? And let's rewrite this denominator as r factorial times, I'm going to group n plus 1, and then we still have that minus r hanging out, and that's all n factorial. Cool so far? All right. So now, choose r. And that's what we were supposed to prove. Cool, cool? All right, so now if we were to take a look at the combinatorial version of this proof, then looks, it's a little bit different. What we would do is, again, we want to let n and r belong to the positive integers, with r being less than or equal to n. Now, suppose S is a set with n plus 1 elements. So here, just to remind you of the formula, so we're talking about sets now, kind of like we did this thing up here, the set A and then the A and not B and all that good stuff. So S is a set with n plus 1 elements. The number of subsets of S of size n, or sorry, size R, my bad, can be calculated by thinking of S as containing two pieces. So one of the pieces is going to have n elements. So call them, x sub 1 to x sub n. Now the other one is just going to have one other element, which would have to be what? Beautiful, x sub n plus 1. So let's write that in. So splitting, or really partitioning into two pieces. One piece has n elements. And these elements were x1, x2, all the way to xn. The other piece has one element. X sub n plus 1. So what was the whole size of S? What were the total number of subsets of S? Beautiful, it was over here, right? Subsets of S of size R. So basically, let's check it out. So the subset size, we're choosing R elements. So if we take a look at any subset of S with R elements, it's either going to contain the x sub n plus 1 or it doesn't, right? Because we've split S. So if it contains that element, then it contains R minus 1 elements from that other set, which was x1, x2, all the way down to xn. Cool? Because we're only talking about that one x sub n plus 1. So by the addition rule, what are we going to have? We'll have a total number of subsets of x1, x2, dot, 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 down to xn, and x sub n plus 1 included in there. And that's of size R, basically what we just wrote out. And that has to equal to the number of subsets of x1, x2, all the way down to xn. And that size has to be r minus 1 plus the number of subsets of x1, x2, all the way down to xn of size r. Because if the set doesn't contain x sub n plus 1, then it has to be a subset of size r, a set of size r that you're choosing from x1 down to xn. So the set x1, x2, dot, 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 down to xn, and then including the x sub n plus 1, has n plus 1 choose r subsets, right, of size r. The set x1, x2, all the way down to xn is going to have, good, n choose r minus 1 subsets of size r minus 1. And finally, x1, x2, all the way down to xn has n choose r subsets of size r. So, by the way, these were all from a theorem in 9.5. That type of thinking. All right. Thus, n plus 1, choose r, has to equal to n choose r minus 1 plus n choose r. Cool, cool? And that's what we wanted to show. All right, so now let's take a look at x plus 2, the quantity cubed. Now, x plus 2 cubed is equivalent to x plus 2 times x plus 2 times x plus 2, because exponentiation is repeated multiplication, right? So now if we're going here to look at this, and we kind of went the old school route, right? Looking at x plus 2 times x plus 2, we would get, and this is writing it out in a form you're not used to so we can show something. So x times x is our x squared plus x times 2 plus 2 times x plus 2 times 2. Cool so far? And then we still have an x plus 2 we've got to multiply to that. So now what's going to happen, well, if I were to just split that apart, so it would be x times x plus x times 2 plus x times 2, I'm going to go ahead and commute those, plus 2 times 2 times x plus that whole thing again, x times x plus x times 2 plus x times 2 plus 2 times 2, and that's times 2. That's just the distributive law. So now we'll get x times x times x, right? Plus x times 2 plus x times x times 2 plus 2 times 2 times x, and then plus x times x times 2 plus x times 2 times 2 plus x times 2 times 2 plus 2 times 2 times 2. Sorry, that was kind of messy. Whew! So we have some like terms, don't we? We've got 2 of those x times 2's. We have 2 of those x times, or sorry, 3 x times 2's, right? And then we've got 3 of these x times 2 times 2. So what ends up happening is this. We're going to end up getting, we're looking for these coefficients here, right? And so if we look at the coefficient of the x cubed, right? That's going to be x cubed times 2 to the 0, because we want to include both a and b in here. The a being x, the b being 2. And then we had 3 of the x to the 3 minus 1 times 2 to the 1. So do you see how the power of 2 is increasing and the power, I'll just write this as 2, the power of the second one is increasing and the power on the x is decreasing. And then we had 3 of the other ones, which was x to the 1 and then times 2 squared. And we had 1 of the 2 cubes. And so using the green here, you can see the coefficients that from Pascal's triangle. Now, if we wrote this in the combinatorial form, this could be the equivalent. So we've got a cube here, right? A cube. And so n is 3. So n is 3. So 1 is the same as n choose 0, right? So we would have n choose 0 x to the n minus r. Well, we'll do it in terms of 3, sorry. 3 choose 0, x to the 3 minus 0 times 2 to the 0, plus 3 choose 1, which is 3, x to the 3 minus 1, 2 to the 1, plus 3 choose 2, which is 3, right? And then x to the 3 minus 2 times 2 squared, and then plus 2 cubed, which of course is 8, right? But I'll just keep it as 2 cubed. So at the end of the day, expanding this, we would have x cubed plus 6x squared plus 12x plus 8. Cool, cool? And our coefficients are given by, oh, and I didn't write it in this one, my bad. Move this over. And then this one would be 3, choose 3, which is 1. So these are the coefficients given us by Pascal's triangle. So now the binomial theorem, using the binomial theorem on this, gives us that a plus b, so a and b are real numbers, and we've got a non-negative integer n, all right, so they're raised to that power, is equal to the summation from k equals 0 to n of n choose k, a to the n minus k times b to the k. But that's just what we did right here, right, with the powers. So one of the powers, you know, starts high and goes down to 0. So I should have actually also, just to line this up nicely, I should have said times x to the 3 minus 3, which is 0. So x to the 0 is 1 times 2 cubed. And then you've got your binomial theorem. Isn't that groovy? So definition, for any real number a and any non-negative integer n, the non-negative integer powers of a are as follows. A to the n is equal to 1 if, of course, n is 0. You could also think of it as a times a to the n minus 1 if n is greater than 0. So we'll be using this in the proof of the binomial theorem. Aren't you excited? All right. So here what we'll do is we'll do this by induction. So suppose a and b belong to the real numbers, and we'll let p at n be the equation. I used to really dislike proof by induction, but I love it now. I know I'm weird. So p at n is the equation a plus b raised to the n, which is summation k is 0 to n, n choose k, a to the n minus k, b to the k. Where n and k are non-negative integers. The reason they're saying non-negative is because they can be 0. And k has to be less than or equal to n. So our basis step we got to make sure that since we're starting at 0, we got to make sure that p at 0 is true, right? So if we look at the left-hand side of that equation, p at 0 would equal to a plus b to the 0, which is 1. The right-hand side for p at 0. So now that kind of uglier side, right? We're going to have the summation as k goes from 0 to 0 of 0 choose k, a to the 0 minus k and then b to the 0. So if we were to expand that out, right, k has to be less than or equal to n, right? So this would have to end up being, so here, this is where we plugged in, so p at 0, this is where we plugged in the zeros, right? And I should have left this as k, sorry. Now, the only way for this to make sense is if k is 0. So you would end up with, because of the conditions, the premise, that k is less than or equal to n. So the only value k can take on, since it's non-negative, is 0. So 0 choose 0, a to the 0 minus 0, b to the 0, which is going to be 1 times 1 times 1, which is 1. And so that checks out. The basis step is true. So the inductive step is next on our agenda. Aren't you excited? All right. So we're going to let m belong to the integers such that m is greater than or equal to 0. So it's an integer that is greater than or equal to 0, non-negative integer. Suppose p at m is true. And so what does that mean? That would mean that a plus b raised to the m would be the summation as k goes from 0 to m. And then we would have a to the m minus k times b to the k. Cool so far? Just put in m instead of n. Now, we need to show that this is true for m plus 1, right? So let's check it out. Let's take a look at what we have. So a lot of times, why don't we see what a plus b raised to the m plus 1 looks like? So this was, just so we can keep track, this right here was p at m. Now, a plus b to the m plus 1 will be the summation as k goes from 0 to m plus 1, m plus 1 choose k, a to the m plus 1 minus k times b to the k. This is our p at m plus 1. So using this little useful definition here, right? we're going to rewrite a plus b to the m plus 1 is a plus b to the 1 times a plus b quantity to the m, right? You would get 1 plus m, which is m plus 1. So by substitution from our inductive hypothesis, right, we could say that a plus b to the m plus 1 is equal to a plus b to the 1, right, times the summation as k goes from 0 to m of m choose k times a to the m minus k times b to the k. So just to keep track, this right here is a plus b to the m. And then, of course, this first one was a plus b to the 1. So it's really kind of groovy right here what we're doing. So when we do this, we can use the distributive law, right, to say that this is equivalent to a times the summation. K is 0 to m choose k, a to the m minus k times b to the k, plus b times the summation as k goes from 0 to m choose k, a to the m minus k times b to the k, just by distributing the a plus b through, or distributing the summation through the a plus b. Now, let's see what would happen if we put these into one, that brought the a in and then the b in. We would have the summation as k goes from 0 to m of m choose k. A is now going to be to the m plus 1 minus k because of that a to the 1 factor, and we'll still have b to the k. And the second one will be, as we go, k goes from 0 to m choose k, a to the m minus k, and now b will go to the k plus 1. Cool so far? All right. Now this all looks really great, right? But we want m plus 1s, right? Because we want to, wherever there was an m, we want there to be an m plus 1. So that first summation has m plus 1 in the power for a, but the second one does not. So let's take a look at this second summation, all right? And what we'll do is a little trick. We're just going to let j, which is a dummy variable, all right, which means we can switch it around. It's just temporarily serving for us to algebraically manipulate this summation. So j equal to k plus 1. So if j is equal to k plus 1, and I isolate k, that's going to be equal to j minus 1, correct? Cool. All right. So our summation as k goes from 0 to m, I'll just rewrite it, of m choose k, times a to the m minus k times b raised to the k plus 1. Okay, so we've got this summation. It's going to go to m, but let's take a look here. When k equals 0, j minus 1 would equal to 0, right, from that equation up there. And so j would therefore equal to 1. So j will go from 1 to m. And then we will have m choose j minus 1. A will be raised to the m minus j minus 1, that quantity, and then b will be raised to the j minus 1. And then we have that plus 1. So wherever there was a k, I just put in j minus 1. So that was for when k was 0, right? I set j minus 1 or k equal to 0. This here had these items had k's, and that's where our j minus 1s went. Groovy? All right, so next up, let's see what we have going on. Sorry, my necklace was clanking, so I'm just going to put this aside. And sorry, I don't want you to think that we're equaling that little side note. Okay, so this in turn will be equal to the summation as j goes from 1 to m of m choose j minus 1. This will be a, I'm going to switch it around because we want m plus 1s, remember, a to the m plus 1 minus j, and then b to the j minus 1 plus 1 is just b to the j. Now, j was just a dummy variable, right? So since j was a dummy variable, we can replace j by k. So we will end up with our summation, original summation there, will be equal to the summation from k equals 1 to m of m choose j, k minus 1, a to the m plus 1 minus k times b to the k. Cool so far? So all of that, remember, was this one up here. So now we've matched the powers on the a and the b to the summation that's on the left here, okay? So let's go ahead and figure out what we've got, putting it all together. So a plus b raised to the m plus 1 is equal to, so we had that summation on the left, summation from k is 0 to m, and that one had a to the, well, m choose k, a, that was m choose k, right? Yep. To the, I'm going to put quantity m plus 1 minus k, b to the k, plus this new summation, which starts at k is 1 and goes to m. And then we had the m choose k minus 1, a raised to the m plus 1 minus k, and then b raised to the k. Groovy? All right. So we want to get these to be the same index. So if I take a look here with the first one, I can rewrite the first one as the 0th term in the sequence plus the summation as k goes from 1 to m of the rest of it. So if k is 0, I will have m choose 0, a raised to the m plus 1 minus 0, b raised to the 0, plus the summation from k equals 1 to m of m choose k, a to the m plus 1 minus k times b to the k, plus the summation from k equals 1 to m of m choose k minus 1, a to the m plus 1 minus k, b to the k. So all I did here is I put together this single summation as the summation when k starts at 1 and goes to m plus the 0th term of the sequence. Cool? That plus is in there. All right, so now m choose 0 is just 1 times a to the m plus 1 and b to the 0 is 1. Now I've got a and b as factors, right? And they are to the same power. So I can within that summation, within that summation, I can factor out from the combinations, I can factor out those products. So we'll have the summation as k goes from 1 to m of, I'll do the combination expressions first. So we'll have m choose k plus m choose k minus 1. Those will be times a to the m plus 1 minus k times b to the k. But, we have to think about what's happening in that second summation. So right here, right in here, k has to be equal to the m plus first term for us to have our m choose m, right? To have that last piece of the formula. So I'm going to go ahead and write that as plus m choose m plus 1 minus 1 a to the m plus 1 minus quantity m plus 1, and then times, sorry, it's smushed here, times b to the m plus 1. Those are all in for k on that m plus first term. So we took out that 0th term, and now we got to take out the m plus first term because that summation is only going to go to m, right? So let's see what we have now. This is going to give us a to the m plus 1. From all that stuff in the purple, we're going to get times 1, because we'd have an m choose m, and then we would have a to the 0, so that'd be times 1, and then we'd have b to the m plus 1. Cool so far? Cool so far? Awesome. And then we will have that summation as k goes from 1 to m. Beautiful. M plus 1, choose k. So, using Pascal's formula, this sum is equal to this combination. All right. And then we have our a raised to the m plus 1 minus k times b to the k. M plus 1, choose 0, times a to the m plus 1. So I'm letting k equal to 0 to see what we get. That's going to equal to what? 1 times a to the m plus 1 times 1. So I'll get a to the m plus 1 and m plus 1, choose m plus 1. If I now let k equal that m plus first term of a to the, that'd be m plus 1 minus m plus 1 times b to the m plus 1 is just going to be b to the m plus 1. So now I can change the summation, right? Because I have those two terms. And actually, my bad, what did I do? This here, I'm going to do this in red, sorry. This should not have been a times, this should have been a plus. So plus this here. Perfect. So I can start the summation at k is 0 and end the summation at k is m plus 1, and we'll be good to go. That's what we needed to show. So that's going to equal to the summation as k goes from 0 to m plus 1 of m plus 1, choose k, times a to the m plus 1 minus k, b to the k. And that's what we wanted to show. Beautiful, huh? All right, perfect. Now let's use the binomial theorem to do some stuff. So if we do it for a straight up expansion, I mean, see here that our a is equal to u squared and b would be equal to negative 3v. So I can have it as a plus in between. So, and then our n is equal to 4 because it's raised to the 4th power. So using that binomial formula, we would have u squared minus 3v raised to the 4th will equal 2. So this would be 4, choose 0. And we would have our a, which is u squared, would be raised to the 4 minus 0, sorry. And then our b would be raised to the 0. So that'll give us our first term, plus 4, choose 1, u squared raised to the 4 minus 1, negative 3v raised to the 1, plus 4, choose 2, u squared raised to the 4, minus 2 negative 3v raised to the 2 plus 4, choose 3, u squared raised to the 4 minus 3, negative 3v raised to the 3, and the last one would be 4, choose 4, u squared raised to the 4 minus 4, which of course is 0, and then we would have negative 3v raised to the 4th. So putting that all together, 4 choose 0 is 1. U squared to the 4th is u to the 8th. Negative 3v to the 0 is 1. And then we'll have 4 choose 1 is 4, right? U squared cubed is u to the 6th. And be careful, you're going to have that negative 3v raised to the 1. So we'll simplify that in the next step. So we'll have a minus for that term. Plus, we will have 4 choose 2 is 6. U squared squared is u to the 4th. And then we'll have negative 3v squared. And then 4 choose 3 is back to 4. U squared to the 1 is u squared. And then we'll have negative 3v cubed. And then 4 choose 4 is 1. U squared to the 0 is 1. And then negative 3v to the 4th. So simplifying, we'll have u to the 8th minus 12 u to the 6th times v plus, so negative 3v squared is positive 9v squared. 9 times 6 is 54. U to the 4th v squared. And then the next one will be a minus because we'll have a cube on that 3. Negative 3 cubed is negative 27. And negative 4 times, or negative 27 times 4 is negative 108. That's going to be u squared v cubed. And then we'll have plus 81 v to the 4th. And we're done. Cool, cool? Awesome. All right, so now find the coefficient of the term x to the 7th and 2x plus 3, that quantity to the 10th. So x is to the 1 power, so you want to have it where your you'll have a situation where you have 10 minus 3 for the x term. So what will happen is this. That term will be 10 choose 3, because that's going to give us our 2x raised to the 10 minus 3, and then we'll have 3 raised to the 3rd. And so 10 choose 3 is going to be what? 10 factorial, 3 factorial, 7 factorial, which will be 10 times 9 times 8. The 7 factorials will cancel over 3 times 2. 3 goes into 9 3 times, 2 goes into 8 4 times, 10 times 12 is 120. That's just a little side note. So we'll get 120, and then 2 to the 7th times, let's see, 2 to the 6th is what, 64? I'll just write it out. 2 times x will be to the 7th, and then we're going to have our 3 cubed, which is 27. That ends up being, when I multiply the 120 and the 27, I got 3240 times 2 to the 7th times x to the 7th. And 3240 times 2 to the 7th is 414,720 times x to the 7th. So the coefficient is 414,720. Cool? So that's kind of nice. You don't have to expand the entire binomial sum to find that term. Okay. Now this next business is expressing the sum in closed form. Basically, that means without using a summation symbol and without using a ... So you don't want to you want to get it to be binomial, right? So let's take a look at what we have. We have a summation where we only have an x raised to the 2r. Now, remember that the general binomial formula, right? Way back here, way back when, right here, looking at our n's and k, in terms of n and k, you have this. So when we look at this in terms of n and r, let's see what we've got. So just on the side, the summation from r equals 0 to n of n, choose r. I'm just going to write it as a raised to the n minus r times b raised to the r. That's what we want it to look like, because that is going to equal to the quantity a plus b to the n. So that's the evil plan. So working on it, how could we rewrite, this x squared business, this x raised to the 2r? So first of all, we could say, hey, this is the summation as r goes from 0 to n, choose r, of x squared to the r. Cool so far? Now, this is a finite sum, correct? So 1 raised to any non-negative power, non-negative integer power, is just going to be 1, right? So I could write this as 1, and what's the other thing I need? N minus r. So putting it in the right order, I would have the summation as r tends from 0 to n, or goes from 0 to n, of n, choose r, and then 1 raised to the n minus r times x squared to the r. So that in turn is going to be 1 plus x squared to the n. Pretty cool, huh? I hope that you enjoyed the show. If you like what I'm doing, please subscribe, and I hope you have a wonderful rest of your morning, afternoon, or evening. Bye.